So, good evening and welcome to this Saturday's webinar series by IITACB. And today we have with us Professor Sai Gautam Gopalakrishnan as a speaker, and he is going to talk on using machine learning to advance materials design. And we have Dr. Trapti Kalra as the moderator. So, let me briefly tell you about the speaker today. So, Sai is an assistant professor in the Department of Materials Engineering at IISc. So his research focuses on applying computational material science, thermodynamics, and kinetics to understand and predict materials behavior. So before joining IISc, Sai was a postdoc in the Department of Mechanical and Aerospace Engineering at Princeton. And he completed his PhD in the Department of Material Science and Engineering in MIT. Prior to his PhD, he has earned a dual degree, again in metallurgical and materials engineering from IIT Madras. A little bit about the moderator, whom we have heard as a speaker last month. So Trapti is a well-rounded technology leader and business executive with a broad spectrum and experience in P&L, people and vendor leadership, and leading global IT strategy and transformation. So her focus is on applied AI and generation AI and quantum computing hands-on at IBM. So Trapti spends her free time mentoring and advising startups and exploring AI and genetic workflows for science. So with this, I hand over the stage to Sai. Over to you, Sai.
Thanks, Sujo, for the nice introduction. Let me share my screen. Yeah, and then go to the sort of PowerPoint mode. Okay. Okay, so I hope all of you can see my screen, and also my audio is fine enough. So let's get started. So this talk is going to be an eclectic mix. So I wanted to give a brief sort of history of how modeling and sort of simulations and also machine learning has evolved along with materials design or material science in general. And what are some of the sort of recent advancements in modeling different types of modeling materials. So I'm Sai Gautam Gopalakrishnan. I know that's a long name, so you can call me Sai. And before I get started, just a set of acknowledgements. This is my group, research group. We took this picture about a week back, so this is fairly recent. So thanks to them for their contributions in getting the sort of research done in the group. Some of the funding agencies and also the supercomputing resources that we need access to get the job done. All right, so I know that several of you are not who don't work in the field of material science. So so for those of you, the question is, why bother about material science in general, right? So to answer that question, if you think about any kind of major technological device or application, its performance is almost always determined by the kind of materials that you use in that application or device. So I work broadly in the area of energy materials, so batteries and photovoltaics and hydrogen generation. So if I were to give an example from batteries, right? So in a battery system, you really care about the amount of energy that you can store within a battery. So that's quantified by energy density, for instance. And we also care about how quickly you can extract that energy. Which is typically quantified by power density, the power performance of a battery. So if you think about energy density, that generally comes from voltages. So if you can store electrons at a higher voltage within a battery, you can typically store more energy in a battery. And those voltages are directly proportional to reaction energies, so reactions that are happening within your battery system. So those are key material properties as well. So stability of the materials also govern how long your battery can be cycled. And ionic mobility, so how quickly ions can move within a solid, really dictates how much power you can extract from a given battery system. So if you take batteries, a lot of its key performance metrics come from materials that are being used and their properties, right? And this is not just isolated to batteries. So if you think about photovoltaics, right? So you typically need a semiconductor to absorb sunlight and then generate electrons and holes, and those electrons and holes are used in your external circuit to power some device, right? So you almost always need a good material with a good band gap so that you can absorb that sunlight. You also need that material to be quite resistant to formation of defects within that material, because we have defects, then these electrons and holes can get scattered. So you may not be able to collect them in your external circuit. So so even in a photovoltaic, the performance of that photovoltaic device is really dependent on the kind of semiconductor you use and its specific properties. So materials are crucial in any technology or application or device that you develop, that you already have or that you develop in the near future. And the sort of key message here is, if you use better materials, you almost always tend to get better performance in whatever device or application that you're using, right? So that's why material science is quite important. Now, the second question is, why care about machine learning, right, when it comes to material science? Now, this graph sort of shows your different technological areas and the time it took for them to go from sort of inventions or sort of prototype stage to eventual market deployment and commercialization. That's indicated by the yellow bars here. And these are fairly wide set of technology areas. So you think about classic technologies like cars, modern ones like mobile phones. I don't know how many of you still use video cassettes. I mean, these were a big thing in the 90s and the 2000s, early 2000s, right? So those are a big technological area. And LED lighting, which is relatively recent, which has entered most of our homes in the form of televisions, right? You see that most of these technologies take several decades, right, to go from invention or demonstration at a prototypical stage all the way to commercialization. So this innovation cycle is even slower when you think about energy sector, particularly energy generation. So think about nuclear power. Gas turbines are used in in coal power plants and so on. Photovoltaics are windmills, right? So the innovation is even slower when it comes to energy generation sector, and we need more rapid or faster innovations in the energy sector so that we can transition towards sustainable use, right? So the key and one of the key sort of bottlenecks in the acceleration or not of a given technology area is the availability of good materials for that technological area. So here is where, if we can somehow accelerate the process of discovering new materials or better materials for a given technology area or application domain, we can actually accelerate these innovation cycles. So basically reduce the time it takes from innovation all the way to deployment. And this is where machine learning can play a key role, because using machine learning, you can actually model materials a lot better. So understand their behavior of a specific material a lot better. Or you can also predict properties of a wide range of materials a lot faster. Thereby, you can try to see which materials are more promising compared to the others. So machine learning can play a key role in trying to accelerate this whole innovation process. So we now kind of understand why material science is important and why machine learning is important within material science, right? And the sort of big boost or big look towards material science, big look towards machine learning within material science, I would say started around 2011 when the US government announced this whole materials genome initiative. So machine learning as a sort of topic started picking up in the early 2000s again. So it was mostly dormant in the 60s to 90s. But it started picking up in the early 2000s, and sort of material science was a little slow to get to it. But this announcement of characterizing different materials by their genome, just like how you can characterize different biological systems using their genomics, was the big driver which sort of forced material scientists to take a look at how machine learning tools can be used for materials discovery and innovation. So with that context, I just wanted to give a sort of an evolution of how modeling or sort of simulations, computations within materials has evolved over the last century or so. Because machine learning may be a fairly new thing to material science, but modeling in general is not new. It's a fairly old area. I would say the one of the starting points of modeling within materials is basically the formulation of what is called as Lennard-Jones potential. So it's a functional form of an interatomic potential. You typically use interatomic potentials to study materials behavior under large scales or long times. And Lennard-Jones came up with a very easy to understand, very simple functional form by which you can usually model closed pack systems quite well. And this was done almost a century back in 1924. And this, I would say, started the field of modeling in materials. Right? The next big breakthrough took some time, so it took almost quarter century later, which is when Alder and Wainwright here demonstrated actual molecular dynamic simulations for a hard sphere system. So until then, in general, computers were very scarce. I mean, you needed whole buildings to function as a computer. They are not as small as your cell phones these days. So you really needed large scale resources, and Alder and Wainwright basically assembled these resources and perform molecular dynamics, which is basically solving Newton's equations on how atoms can move within a given solid. And they performed these molecular dynamic simulations and showed that it could actually work on a hard sphere system. So there are several approximations, but it's a good sort of a demonstration that computers can be used to study materials. The next innovation came in the 60s when the formulation or proof of density functional theory actually was wrote into existence by Hohenberg and Kohn. If you look at most modern computational material science or usage of big data within materials, almost always the data comes from density function theory based calculations or DFT based calculations. So DFT is the bedrock for all of those, and that was formulated about 60 years back. But large-scale DFT calculations were still quite rare. In the 60s, people are still understanding how to use this new framework and so on. The mid-1970s marked a new direction of modeling materials, which is in the form of lattice models. Most materials in microscopically, they form very ordered configurations, very three-dimensionally ordered configurations, which we typically call as lattices, right? So lattice models basically try to understand how different configurations can play a role in the properties of a given lattice. And in 1975, this is when a formalism called cluster expansion was developed for material science, and this has paved the way for predicting phase diagrams and long-range behavior of several materials in the ensuing decades. So this was a major landmark as well. And then 86 is sort of a rough follow-up to 1924 here. This is when Stringer and Weber put together an interatomic potential for silicon. So silicon, as you probably know, is a very important material for semiconductors, for photovoltaics and so on. And it is still industrially used to understand how silicon behaves, both in its crystalline phase and its amorphous phase. 1996 is follow-up to 1964 here. This is when Purdue, Berkeley, and Ernst-Hoff, the three of them put together an approximation for density function theory that allowed the large-scale use of density function theory. So from the 60s to 90s, DFT was predominantly used by physicists and chemists who understood how to code and also understood the nitty-gritty of DFT. So it was not used by a large pool of people who didn't really understand the formalism or the codes, right? This TBE framework allowed a large set of users to start using DFT, even if they were not expert coders, nor if they understood the theory 100%. So this was a major development in making DFT accessible to many material scientists and other scientists around the world. 99 is when the projector augmented wave method was implemented in the tool called VASP, VASP. This is important because the projector augmented wave method increases the accuracy of DFT calculations in predicting material properties. So this is quite an important innovation. And it was plugged into the VASP code, And WASP had 100 users probably in 1999. Now it has tens of thousands or hundreds of thousands of users, if I'm not wrong. So the code became largely popular because you could use it in a fairly easy fashion with fewer handles, and you could get fairly accurate results. 2003 is another big year for sort of data science to play a role in material science. So there were two papers where both the authors demonstrated the first instances of using what are called high throughput computations. So until the early 2000s, if you were doing DFT simulations or DFT calculations, you would pick up one or two systems and then do maybe 10 calculations, 15 calculations on them, and then try to understand, okay, how these systems are behaving and so on. That would be a paper or a patent or whatever. 2003 was a breakthrough year in which these two papers showed that you can do almost 10,000 calculations in parallel, so across almost 10,000 systems. So this was a huge landmark because it showed that you can create automatic workflows that can be used to run DFT in a fairly non-human managed way and generate data in a large scale. And for any machine learning model to work, machine learning workflow to work, you need data. Data is the fuel. So 2003 was the turning point in generating that fuel. 2007 is once again a follow-up to 24 and 86 with an interesting twist. So it was in the mid-2000s that neural networks became quite popular again in the sort of regular computer science domain and computing vision and whatnot. These two folks, Baylor and Parinal, thought, okay, let's use neural networks, but to model materials in the form of developing an interatomic potential. So they developed interatomic potentials with artificial neural networks, which were quite a new thing to be used in materials. And this has spawned a way of rapid development in the field of interatomic potentials within materials with increasing accuracy and ease of use also. So 2011 to 18 was the period of the first US Materials Genome Initiative. This initiative enabled the creation of several large-scale computational databases of different systems, different properties being calculated, and so on. So the US government sort of gave a lot of money to several research groups, which then invested in developing workflows, actually doing the calculations and generating the data. The good thing is all of these data are open source, so which means that we can also use them to build our own models here. So that was 2011 to 18. And 2018 was another sort of big breakthrough, which is when graph neural networks started making an appearance within materials modeling. I'll describe this later in the talk today, but graphs represent a very sort of intuitive, very easy way to model a given material, a given three-dimensional lattice. And we have seen that ever since graph neural networks were introduced to model materials, the kind of accuracies that we can get within our machine learning models and the kind of models that we can actually create has grown immensely, right? So this is another sort of major landmark, and I hope that in the near future we will get more such landmarks to sort of populate this way. So I hope that going forward, I won't lose out any of the history, but the future or the near present is going to become more and more compressed. Okay, so with that context, what are some of the typical sort of kind of machine learning that you do in material science? The first one is the classic sort of regressions or classifications. So what I mean by regressions here is you want to be able to predict properties of several kinds of materials in a fairly simple fashion, or at least fairly quick fashion. And we try to create models that can do that in a fairly quick fashion. So that's one type of machine learning that we typically do. The second one is constructing interatomic potentials. So this is when we want to study one material or a small collection of materials in a fairly deep fashion and in a fairly accurate fashion. So so for these materials we typically want to model their sort of kinetic behavior, their defect behavior, some kind of diffusion or dislocation motion and so on in that material very accurately, which means that we need to model their potential energy surface very accurately. So So there are a lot of machine learning work which tries to create very accurate interdynamic potentials. Third one is sort of more advanced topics. I'll also cover a bit of this in the last half of my talk. Where this is where diffusion models are being used to generate crystal structures. Language models are also being used that can leverage sort of the framework of large language models, ChatGPT and so on, to generate crystal structures, and also transfer learning, where you can train a large scale model and then transfer most of the learning that you have gotten to a smaller data set where you don't have a lot of data. So these are the sort of three types of machine learning. I'll try to cover a bit of all through my lecture and try to give some perspective along the way as well. All right. So as I mentioned before, for any machine learning workflow to work, you need data. Data is the fuel. If you consider machine learning as the engine, data is the fuel, right? So where does the data come from? Most of the data comes from sort of density function theory calculations. That's the bedrock. You can also use molecular dynamic simulation that's typically done through LAMS software. There are also high throughput experimentation that is beginning to generate data. I don't think we are at a scale where we have hundreds of thousands of data points yet. We probably have about a few thousand data points with respect to high throughput computing. So there are several databases that are available. So these four are computational databases. NIST is partly computational, partly experimental. It has nice reaction energies. ICSV is it's almost fully experimental. It has a lot of structures. And HTM is an experimental, high throughput experimental database that is developed by National Renewable Energy Laboratories in India. Okay, and if you are sort of if you are wondering where I can get access to all these data, right? So there are several databases that have developed different data. One useful thing to keep looking at is MadBench or MadMiner. These are basically repositories or leaderboards where they the sort of maintainers list a lot of data sets that are now available for use. So these are cleaned data sets, so you don't have to worry about whether the data is correct or not. Sanity checks have been made and the data is fully cleaned. It's an easy to use form. And this leaderboard basically tells you which models are the best performing for a given data set. So these two things can be, you can keep your eye on these two things to have an idea of where things are going. So with respect to programming languages that are typically used for implementing these machine learning models, almost always the data organization is done through APIs. So you use APIs to get data from a repository, and you typically run those or call those API functions using Python. And for most of machine learning, we typically use Python. So scikit-learn for the classical simple machine learning models, probably TensorFlow for the neural network models. Okay. So with that, before the sort of break, I'll give a few examples of clashing machine learning models and how they have been used in materials. So give you a few examples of their use cases. So to begin with, I'll briefly describe how classic machine learning works and then give you the examples towards the end. So if you think about classic machine learning models, about whether a model is linear or non-linear in its functional form. So if you think about the relationship between a target property and the variable that you want to make predictions with. So this is the variable that is under your control. This is the property that you want to predict. If the target property is roughly linear with respect to your independent variable, then a linear model makes sense, right? If the target property is non-linear, I mean this is almost quadratic in nature, then you need a non-linear model. So if you were to take a linear model, the functional form is fairly simple or intuitive to understand. So you typically have a constant term. You have some weights associated with all the independent variables that you have in play. If you have a non-linear model, you once again have a constant term that is usually set as an offset. But you have a non-linear function here of a's and xi's. This non-linear function can be a simple quadratic, sinusoidal function, exponential function, and so on. Right? And what are some of the popular models for popular linear models? So you can think of linear regression. The name itself gives you the gives you an idea. You can also have linear regression with some constraints, with some regularization. So that's lasso and bridge. In terms of nonlinear models, the popular models are random forest, support vector machines, and k-nearest neighbors. There are also neural networks are also non-linear, but neural networks don't necessarily fall under the classical machine learning category. So they are more modern and they are more complex models as well. Okay, so I'll just give a brief overview of the nonlinear models. So the first one is random forest. So here you have a bunch of trees that make decisions on your data. So whether a data, whether a given data point falls under a certain if-else condition, certain classification. So different trees act on the same data set that you have, and finally they arrive at a set of classifications, which you then have a voting or pooling procedure. And then you make a final result on your data point. So what is this data point corresponding to, right? So this is an example of an ensemble model. So again, each tree has if-else conditions, and there are some pros and cons to using a random forest model. I'm not going to list through. I'm not going to talk through the pros and cons, but you can have a read while I talk about the other models. With respect to support vector machines, here we are trying to form like hyperplanes between collections of data, and then when a new data point comes in, we then try to identify whether it's going to go through these blue spheres or through these yellow spheres. Right? And these are some of the pros and cons of support vector machines. For k-nearest neighbors, here we try to understand how similar or different a new data point is compared to all the data points that the model already has seen. So, given a new data point, the model tries to see whether it should fit in these category A or category B. And these are some of the pros and cons of k-nearest neighbors. So, these are popular sort of non-linear models that are typically used. Okay. So, let me give you a couple of examples of these simple machine learning models for material science. So this is an example that I'm actually a part of. So here we try to predict the vacancy formation energy in oxide perovskites, so AbO3 perovskites. I mean, they had their own applications in water splitting, so basically in hydrogen generation. So the data set was fairly small, so it is only about 341 data points. So this is a small data set, and typically when you have small data set, you want simple models, or you at least want to try out simple models. So we generated a linear model with physically intuitive parameters. So think about bond dissociation. So when you form a vacancy, you are breaking bonds. So bond dissociation plays a role. When you break a bond, you also leave behind electrons or holes within the host material. So the reduction potential also becomes important. How easy is it for the electrons and holes to delocalize within your material? So band gaps become important, and how stable the underlying material. So energy above the hull becomes important. And the model had some performance, and we identified some new candidates for water splitting. Right. So this is a very classic machine learning workflow where we have generated the data set. It's a limited data set, and we use a simple machine learning model, a linear machine learning model, linear regression model with physically intuitive descriptors. This is another similar work. I'm not a part of this work, but this model tried to predict elastic modeling on a bunch of inorganic crystals. So they took a database of about 3,000 points from the materials project database. And this data set contained both bulk modelers and shear modelers. So two sets of elastic modeling. And this model, and the authors generated a support vector machine model. So this is a non-linear model. And it had quite a few descriptors, so about 150 composition and structural descriptors. This model had a fairly reasonable performance, about 0.94 R2 score, and they identified new incompressible materials, so materials with very high bulk modulus. And the nice thing was this work was also experimentally verified. So the authors not only predicted these candidates, but also collaborated with an experimental group and then verified their predictions. So this is another example of a classic machine learning workflow where here the authors didn't generate their own data set. So they took a data set that was built already from computations, but then they built a classic machine learning model, a non-linear model, and then made predictions, trained a model, made predictions, and then identified new materials that can be incompressible. So another example of a classic machine learning workflow in action. So just to summarize, so classic machine learning models have been used in specific property predictions with varied accuracy. They're still being used very much in industry and in academic settings. So before moving to the next topic on graph models, I'll probably stop and then I'll take questions.
Yeah, thank you. Thanks for that, Professor Sai. So you just covered, how from the whole evolution has happened in material science with machine learning. So that's very interesting. So I think I'll just first reach out to the attendees for any kind of questions, and then I have a couple of questions of my own. So Neeraj, I see you have a hand raised in some time. Do you have a question? Neeraj Yadav.
Maybe they're supposed to type the question.
Yeah, they're supposed to type it because he had raised a hand. I just thought. Okay, so there are no questions. Anybody has a question, please type it in the Q&A box. So in the meantime, I'll just start. So you mentioned a lot about, we saw through a lot of research which has happened, all the papers that have come out starting from, let's say, the early 1950s, 60s, and then 2018 onwards when deep learning is really taking its roots. And this is happening, if I look at it, like US has been a big proponent, not just of, so doing some research, but also open source, similarly from UK, other EU nations. So how is the research landscape looking like in India? Would you like to share a bit of thoughts about how this field is emerging in India, how it is shaped up, and where are the key research, you can say, groups, if people are interested to know about more?
Yeah, sure. So in India, I mean, has been a little slow to catch on when it comes to sort of computational material science and also the use of machine learning in material science in general. So with respect to databases, I think we have had a couple of databases that have been developed. So the one that I can think of is from IIC itself, called Anant, which is predominantly developed by Professor Abhishek Kumar Singh in the Materials Research Center. So Anant is a database of two-dimensional materials. So he has basically done high throughput calculations of several 2D materials and then tabulated their properties in that database, right? I think Professor Umesh Wagmare was also involved in one of the database developments, Umesh Wagmare from JNC, but I cannot quite recollect the database name or the effort. I think it was on ferroelectric materials, if I'm not wrong. So India has been a bit slow in terms of developing databases, but with respect to usage of many of these machine learning tools, such as graph networks, deep learning models in general, I think we are catching up quite well to the US, European Union, and also UK. There are several groups in most of the older IITs that are taking a lead. Some of them are actually using experimental data to create machine learning models. And some of them, use these open source databases, right? And then they create their own unique interatomic potentials, unique graph models, and so on.
Okay.
Yeah.
Great.
So I'd say old IITs and then IAC and JNCSR. These are the sort of main institutes to look out for. Yeah.
Okay. Professor Anil Prabhakar has a question.
Yes.
He's saying that in this approach, are we not going to be limited by the number of DFT or other input models?
Yeah, so it's not just the number of DFT calculations, actually. So material science as a domain is fairly data limited, right? If you think about how much time it takes to generate data, be it computational or experimental, generate a single data point. It's actually quite long for material systems, because material systems take a lot of time to be synthesized and then characterized and make sure that you have the right material, and then you have to go towards measuring their properties. And property measurements also take time. So if you think about all the big data sets, the biggest data sets of materials properties are about 130,000 data points, 130,000, 140,000 data points. So we are not a domain that has a large number of data points, even historically or in the near future. So as a community, we almost always have to deal with small collections of data, small collections of highly verified, highly valuable data. So we need to develop models that can learn quickly from these small data points and then, extrapolate to create newer predictions, hopefully accurately.
Sure.
So just to come back to that question, just DFT calculations are not the bottleneck. Even experimental characterization is a bottleneck.
Yeah, I think his point is that, are we not limited by the number of DFT calculations which are limited? So does that limit our ability to do, extensive machine learning across domains?
Yeah.
So,
yeah, I mean, the good thing is, most of these databases have already been developed. So if you look at materials project, right, that has about 150,000 structures. So that's a good enough data set to begin with, right? Many of these databases have also released their trajectory data sets. So trajectories are basically, if you start a structure and then you calculate it using DFT, the structure actually undergoes an evolution before it reaches its minimal energy state, its ground state. So these databases have also released their trajectories, and these trajectories are about million data points and so on. I mean, they may not be million diverse data points. You may have these 150,000 structures which are undergoing relaxation. So let's say each structure has about 6 or 7 images. You very easily reach a million, right? So that's how these data sets are, and they already offer a fairly good starting point for building reasonable models. So we are not at a point where we are highly constrained by DFT. And with the workflows that are now available, even if you want to generate a DFT-based data set, generating like 1,000, 2,000 data points is not that hard these days. So you can create like very small models very accurately as well. I hope that answered the question.
Yeah. There's another question from Satvik Kalra. Is there a way for generative models to design entirely new materials beyond the scope of existing data sets? And if so, how?
Yeah, so I'll talk about it a little bit using diffusion models. Yeah, so there is a way to generate, to basically hallucinate really new materials. So far, the hallucinations have been bad. So it's still a work in progress, but I think we'll get there. I mean, the ChatGPT version 1.0 was bad. It's only version 3 that took the world by storm. So.
Absolutely. We've lived through that, so we all know that. Yeah. Okay, there's a question from Neeraj. Thanks for typing it here. Is there any possibility of predicting performance of advanced materials for supercapacitors and batteries?
Yes, you can. You can make those predictions. I don't know if I have examples of battery materials, but I mean, we work on battery materials all the time. So yes, you can predict the performance of very advanced materials quite accurately. Yes.
Okay, great. I think if there are no more questions, I think we can proceed to the second part. And then after that, I hope by that time we'll have a full clarity of the advanced concepts and we can have a more detailed discussion.
Yes, yeah, sure. So now that we have a reasonable overview of the classical models, let's get into graph models and how they have enabled the creation of fairly advanced machine learning tools and frameworks for modeling and predicting materials. Okay, so if you think about neural networks in general, right? So they are very good at predicting fairly non-linear data. So if you have a non-linear data that sort of looks like this, right? You simply cannot use a linear regression or a simple regression data to model this kind of data set. So you want more complicated models, mathematically more complex models, which is where neural networks sort of fit in. They sort of have this rough architecture, right? So you have a bunch of weights and biases, and then you have activation functions within a neural network, and then more weights and biases before you can make final predictions. So in a neural network, typically you have an input layer, then you have a bunch of hidden layers, right? And then you have an output layer. So this is a predominant workflow of any neural network. So of course, there are pros and cons. The main pro is that they can deal with more and more complex data in a fairly straightforward fashion, and they can be fairly accurate, right? So there are several types of neural networks that exist, but the most relevant for materials is probably graph neural networks. Which combine the modeling of graphs along with neural networks. So let's take a look at how graphs work in general. So if you think about any graph, right? So it has a bunch of nodes, and then it has a bunch of edges that are connecting these nodes. This is in a very simple way how to visualize a graph. Now you can characterize each of these nodes by what is called as a feature vector. So each node, basically a feature vector, characterizes what is there in that node, right? So node 1 is, let's say, blue in color. So x1 can be blue, x2 can be the size of the node, x3 can be the number of the node, and so on, right? So each node has its own feature vector that characterizes it. Now the straightforward analogy between graphs and materials is that you can now think of each node in a graph representing an atom in a structure, right? So atoms correspond directly to nodes, and edges basically represent your bonds between your atoms. So you have two atoms that form a bond, then that bond can be represented by an edge, right? So that's why graphs are a very intuitive way of modeling any given material, because any given material has atoms sitting in discrete positions, and then they have bonds that are forming between those atoms, right? Now, as I mentioned, each node has a collection of properties. So if you think about each node representing an atom, you can now put in atomic properties here. So that can be like, mass of the atom, atomic number, electronegativity, and so on, right? So you now take these graphs. So you have a graphical representation of your data, which is your structure. You put it through a suitable convolutional scheme. Convolutions help you understand your neighboring environments better. We won't worry about the details of the convolutional scheme, out of which you get what are referred to as embeddings. So embeddings are basically vectorial representations of your structure. So they are vectorial representations of your graphs or your structures, and then you feed those embeddings to a feed-forward neural network, and then you train this neural network for any regression or classification task. So this is the typical workflow in a graph neural network. Now the nice thing about graph networks are that they can make predictions at different levels of the network. So you can make predictions at the network level, which is basically structural level. So think of any structural properties that could be, bulk modulus, formation energy, band gaps, and so on. They can also make predictions at an edge level. So for a given bond, so think about bond dissociation energy, cohesive energy, and so on. So those predictions also a graph network can make. They can also make predictions at a node level. So node level can be something like vacancy formation energy, right? Defect formation energy, and so on. So graph networks are quite versatile in that sense. Now, what are some of the pros and cons? So once again, graphs can be highly accurate. We'll talk about message passing in the next slide, and can take into account underlying symmetry of your structure very, very, very easily. Now, there are also cons. So typically, when you have to build graph networks, you almost always need larger storage, so larger memory. And we also need to ensure that graphs retain some of the symmetrical elements within the structure. So that could be invariance, equivariance, and so on. We'll talk about invariance and equivariance a little later. Okay. So one of the key things about graphs is their ability to do what is referred to as message passing. Message passing is basically, so if you have an atom here in position 1, atom 1 can learn about the neighborhood of atom 2, atom 4, atom 3, and so on. So atom 3, 4, and 2 are its nearest neighbors, right? But it can also learn about the neighborhoods of those nearest neighbors by the way of message passing. So how does message passing work? So let's say this is how your graph is initialized. At the end of the first message passing layer, look at the feature vector of your node 1 here. The colors have changed, right? So some of the values of your feature vector has actually changed, reflecting what this node has learned from its nearest neighbors, right? So typically, how does your message passing work? So you take the initial feature vector that is representing your node. You take into account the feature vectors that are coming in from your nearest neighbors, right? And then you have an aggregation, a pooling scheme, and then you have a new feature vector. And then you do this, update message passing for multiple iterations. So if you were to do multiple message passing layers, right, look at how the feature vector of node 1 has changed, right? So initially it was all blue in color. Now it has a mixture of colors, right? So light blue, gray, yellow, and so on, right? So basically with multiple message passing, your individual atoms learn about the atoms that are actually quite far away from their position. So they can learn to capture longer range interactions as well. So this is a very nice feature in graph networks, and this also mimics how materials behave in general. right? So you have atoms forming bonds, but those bonds are also influenced by bonds that are forming farther away, from those respective atoms. So it is important to also capture those longer range effects, longer range interactions. Okay, so let me give a couple of examples of how graph networks have been used to predict material properties first, and then I'll give other more specialized examples. So the first is one of the very first implementations of graph networks for material science is using this crystal graph convolutional neural network, right? So graph refers to graph networks, crystal graph, so graph networks for using crystalline systems, so crystalline lattices with a convolutional neural network, right? So that's how this model was constructed. This is a basically a schematic of this model. And the authors, once they constructed these crystal graph convolutional neural networks, they built multiple models for several different material properties and achieved fairly good accuracies for each of those properties. Right. So this is one of the very first implementations of graph networks in predicting material properties. The second example also used crystal graph convolutional neural networks or CGCNNs. But for predicting shear modulus and bulk modulus. So, and these were properties which were sort of relevant for energy storage. Basically, the authors were trying to identify solid electrolytes that can suppress dendrite formation in solid-state lithium batteries. So, generally, electrolytes that have fairly high shear modulus and bulk modulus tend to suppress dendrites fairly well. So the authors here used a small data set, actually, only about 12,000 compounds, but they were able to generate or train a graph network to be able to predict shear modulus and bulk modulus with reasonable accuracy, right? So this is another example where graph networks can be used to predict material properties. Okay. So just to have a short summary here, graph networks are a very intuitive way to predict or to model materials. And they can give you very good accuracy in predicting material properties with a similar backbone, with a similar architecture. So you don't change the architecture too much, use the same architecture, and then you train on different properties, you can get very, very good accuracies on those different properties. Okay, so that's a brief overview on graph models. Now, let me give you specific examples of how graph models have really influenced advanced machine learning in material science. So the first use case is on interatomic potentials, right? So how have graph models enabled the construction of fairly accurate interatomic potentials? Okay, so the first question is why interatomic potentials in general? Now, most materials do not have a very simple potential energy surface that looks like this. They have a fairly complicated surface that looks like this. So which means you need a complicated model, right? Machine learned interatomic potentials or MLIPs give you that functional form. So they enable you to fit these fairly complex potential energy surfaces in a very simple, trivial fashion. How do MLIPs work? So you have atoms in a structure. So you take an atom of reference, a central atom. You fingerprint the neighborhood of the central atom. So I'm representing that neighborhood by this two-dimensional projection here. So you fingerprint that neighborhood and then feed that to a neural network or another similar architecture, and then you train that neural network to predict energies, forces, stresses, and so on. Right? So that's in a very simple, trivial sense how a machine learned interatomic potential works. Right. So where do graphs come in? So graphs have two powerful features that can really enhance the accuracy of interatomic potentials. So first is what is referred to as message passing, right? So we understood how sort of message passing works in a broad sense in graph networks. So basically you have an atom at the center, it has its nearest neighbors, right? And then as you keep doing message passing, it learns from its farther neighbors, right? So it learns about the environment of its farther neighbors. Now, if you were to use graph networks, this ensures that you can have a fairly small region of influence around a central atom, what we call as a cutoff radius, right? So cutoff radius can represent the nearest neighbors of an atom within a structure, right? So your model takes into account only the nearest neighbors in the first instance, but with message passing, it can learn about its next nearest neighbors, next nearest neighbors, and so on. So the more message passing you have, the more a central atom knows about its farther neighbors. Now, if you didn't have graphs, so if you didn't have message passing, in order to capture atoms that are actually farther away from your central atom, you actually need to construct farther and farther, cutoff radius. You need to use farther and farther cutoff radius. Basically, take into account larger and larger neighboring environments, which makes your model bulky, right? So it makes it very bulky to implement, so very memory intensive, very data intensive, and also decreases the accuracy of such models. So message passing basically ensures that your graph networks can be fairly light and can be fairly accurate at the same time. Okay. MLIPs incorporating message passing, basically graph networks should have higher learning rates, so they should be able to learn from data better and describe long range interactions better, right? So that's on message passing. The second other important aspect that graph networks enable is what is referred to as equivariance, right? So let's take the image of this dog, right? So if you were to understand how this image itself behaves, right? We need to understand that, this image here is just a rotation of this image, right? So both of these images represent the same dog, but it's just a rotated version of one image, right? So if your model understands how motifs can be rotated, right, can be reflected and can be translated, your model can understand several different aspects of your data much better, of your structure much better. So models that can understand rotation intrinsically are referred to as equivariant models, right? So instead of modeling this dog, let's say you are modeling a point in the image, right? Now a point is invariant in an image. What I mean by invariant is it doesn't really get affected by how you rotate. A point is a point, right? So that's an invariant in your image. And models that are invariant do not intrinsically understand how rotations, reflections, and translations behave. And such models typically require more data to be trained, because you need the normal image and you also need the rotated image to be shown to the model for the model to understand, oh, these two are basically the same. Whereas an equivariant model will take just one image and will understand how the rotations will look like. So that's in a very simple image perspective. If you think about simple vectors and scalars, right, that we observe in three-dimensional space, distance metrics are usually invariant. So distance between 2 points is invariant to rotation, translation, reflection, and so on, right? But the vector itself is equivariant. So if you have let's say a change of basis, so if you go from Cartesian coordinates to spherical coordinates, your vector itself will change, but the distance won't change, right? So distance is an example of an invariant quantity. The vector itself is an equivariant quantity. Right? Further, to give an example of materials, right? Energies of a given material are invariant quantities, right? But forces and stresses in a material are equivariant quantities. And for modeling any dynamic behavior in a given material, we need to have high accuracies on forces and stresses as well, not just on energies, right? So if you need high accuracies on forces and stresses, you need equivariant models. And it is fairly straightforward to include principles of equivariance in a graph network compared to a non-graph network, right? So graph networks gives you two main advantages. One is message passing. Second is equivariance. That allows you to construct fairly accurate interatomic predictions. Okay. With that in mind, we have now reached a stage where we can create what are referred to as foundational models or foundational interatomic potentials with graph neural networks, right? So the model that I have highlighted here is what is referred to as MACE. MP0 refers to materials project, 0 refers to the version of the model, right? So this is an example of a foundational model. So what is a foundational model? A foundational model works across, is an interatomic potential that works across a wide range of systems, a wide range of elements, compounds, polymers, intermetallics, and so on. And it works fairly accurately. So it may not be extremely accurate for any given system, but it can at least form a baseline. It can give you a reasonable baseline accuracy upon which you can do your own special set of calculations, or you can train your own special set of models, right? So this MACE model here is a graph neural network model, right? So it uses both the principles of message passing and equivariance. And using these, it was trained on the materials project trajectory dataset, so about 1.5 million structures. And it is able to predict the behavior of a wide range of materials here. So ranging from pure metals here to cathode materials for lithium-ion batteries. So those are usually oxides, phosphates, and so on. These are ammonia borane, so sort of inorganic molecules. And then you also had organic molecules here, like amorphous carbon, so solvent mixtures, dissolutions. So there's a wide range of materials that this foundation model is shown to have reasonable accuracy towards, right? So graph neural networks have made this possible. The sort of one example that I wanted to highlight, which is on prediction of pore bay diagrams. So pore bay diagrams are very important for electrochemistry, corrosion, and in general, anything that involves a solvent. So pore bay diagrams sort of quantify the stability of a phase given some external environment, usually characterized by a pH and an applied potential. And look at how similar the pore bay diagrams are. That is generated through DFT, that's materials project here, and generated through this foundation model, MAZE here, right? So these are fairly accurate, predictions. And this is not actually the be all end all of graph models, graph neural networks and foundation models. So MAZE MP0 came about, was released around September of last year, September 2024. And it is not even the best performing model. There are 6 other models that have beaten its performance, and most of these are based on graph networks. So graph networks have made foundation models to be fairly real, in the sense that we can actually use them off the shelf over a wide range of materials, and we can use this as a baseline tool at least, and we can perform further calculations to improve our own accuracies. And MAZE, ever since it has been released, has been used in other studies immediately. So it has been used to model zeolites, which are structures that are used for carbon capture and so on, hydrogen storage and so on. So these are fairly functional materials. MAZE has been used as a screening tool for cathode discovery for lithium and sodium and batteries. And it has also been used to predict how perovskites, so like perovskites such as calcium titanate, polarize with applied electric fields. So this is a fairly difficult thing to predict using conventional intensity function theory tools, and MAZE is able to do this fairly well. So just to summarize this context, right? So graph networks are in general quite useful to modeling materials, and in the specific case of interatomic potentials, they have sort of opened the possibility of having very accurate interatomic potentials and very good foundational models. So that's on graph networks and interatomic potentials. I'll give you a couple more examples. So one on transfer learning and one on diffusion models. Okay. With respect to transfer learning, so this is again related to one of the questions that was asked during the break about data limitations in material science. And I want to reiterate that materials is a very highly data limited domain, right? So most of the data sets that we have, so data sets of measured or calculated material properties, are usually about 10,000 data points strong, or less than 10,000. And especially if you think about properties that are really important for material performance, this could be ionic mobility within solids, D5 formation within semiconductors, absorption energies within catalysis. These are all highly limited data sets. We don't have a lot of data going on, right? And this really limits the application of deep learning frameworks, right? One way to overcome this data set limitation is using transfer learning. So what do we do in transfer learning? So I'll give you an example of a vision problem here. So let's say you want to distinguish tissues which have cancer and do not have cancer. So this may be a very small data set. So let's say a few thousand data points, right? But in order to train a deep learning model on this, instead of training a model from scratch on distinguishing tissues with tumor and without tumor, you can actually train a model on cat images. So on the internet, you have millions of cat images floating around. So you can take a model and then train it to classify cats and non-cats, right? So you can train a deep learning model and then transfer what the model has learned. So basically you freeze most of the model, right? And then you retrain it or fine tune it on the smaller data set of cancerous tumors, right? And if you do it right, the model will actually be able to classify cancerous and non-cancerous tumors fairly accurately and fairly quickly as well. Fairly quickly in the sense, it can learn on a fairly small data set of images and be able to make predictions fairly accurately, right? So this has been shown to work in vision problems. So the question is, can we now use it for materials as well? So we know that materials is a fairly data limited domain. So can we use transfer learning to first learn on or pre-train on larger data sets and then fine tune on a smaller data set, right? And we thought, okay, let's use graph neural networks because graph neural networks in general model materials well. So maybe we can actually use graph networks to graph neural networks for transfer learning applications as well. Okay, so let's give a sense of how transfer learning can work, right? So I'm showing here 7 different data sets here. These are different material properties. Don't have to worry about the details of these properties. And I'm showing the performance of scratch models here. So these scratch models are trained on a data set of about 800 points. So these are fairly small data sets. So I'm training a model, a deep graph model from scratch on these 800 data points. And what am I showing here? I'm showing the basically the performance of these models. The lower triangles are R2 scores. The upper triangles are mean absolute errors. You generally want higher R2 scores, so blue lower triangles and low MAs, so red upper triangles. So this is the ideal color combination that you want in all of these boxes here. So these are the performance of models that have been trained from scratch on each of these 7 different data sets, right? I can also do transfer learning, so which is what we did here. So what we did is basically pre-trained on one of these data sets and fine-tuned on the other data set here. So the y-axis here shows pre-trained data set, the x-axis here shows fine-tuned data set, and all the fine-tuning was done on the same data set size, about 800 points, right? So basically, you can compare all the scores along any column here, right? So these are all shear modulus, these are all phonon frequencies, these are all formation energies, and so on, right? So what and the yellow boxes here basically show the best performing models, right? So what are some of the big things that we learned from this work? So one is that pairwise models. So basically, if you do pre-training and then fine-tuning, the performance of those models are always better than models trained from scratch. So transfer learning has very, very big utility when it comes to material science, right? So you can pre-train and then you can do fine-tuning and get models that are more accurate than your scratch models. And we found that there are certain properties that models tend to perform better, both scratch and transfer learned models, and certain data sets where the models are not that accurate, right? And this has to do with how the data set itself is distributed within those data sets. Okay, and there are other sort of important things that we noticed. One is that the specific property that you do pre-training on has very little influence on your target property. So what I mean by that is, so let's say you want to predict formation energies. It doesn't matter whether you pre-train on phonons or you pre-train on band gaps, you get very similar performance, right? So this is something that is actually fairly non-intuitive, but it is very important to note for materials. And the other sort of nice thing is there is actually no real symmetry between properties. So if you had, so let's say you want to predict band gaps here, experimental band gaps here. The best model you get is when you pre-train with shear models. So you pre-train with shear models and then fine-tune on experimental band gaps, you get really good models, right? But if you want really good predictions on shear models here, you don't get that by pre-training on experimental band gaps, right? So a data set that gives you best performance when you fine-tune, right, doesn't give you the same performance when you pre-train on it, right? So there is no symmetry between pre-training and fine-tuning data sets. So this is another very important and very nice insight that you can get in transfer learning. Okay, so just a summary of what we learned from transfer learning here. The second thing that I wanted to talk about is you can also use graph networks and the idea of transfer learning to build what are called generalizable models. So in interatomic potential, we call them foundational models. So they work across a wide range of materials. Generalizable models work across a wide range of properties, right? So you want to predict, let's say 15, 20 different properties of a given material. How do you generate a model that works reasonably well on each of those 15 or 20 different properties? And then you can fine tune, you can make that model more accurate on one specific property, right? So we thought, okay, let's try to create these more generalizable models. And we thought maybe the best way to create these generalizable models is to train on multiple properties at once. So we basically, the idea is that we take a graph network, right? And the prediction head alone, we modify it so that you can actually predict multiple properties at the same time, which means it can also be trained on multiple properties at the same time, right? So in practice, how the way we did it was we took our 7 data sets that we had before. We built a cumulative data set here, and then we modified our loss function and so on. These are details. These are not very important. But the sort of key takeaway message is that if you take this multi-property pre-trained model and then try to make predictions on something the model has not seen at all, right? So far we looked at 3-dimensional material properties like band gaps, formation energy, shear modulus, and so on. So we took our multi-property model and then tried to make predictions on band gap of 2D materials. So the material class itself is completely different, right? And the property is also fairly small. So it's only about 1,100 data points or so, right? So we took our MPT model and the MPT model once again gave the best performance amongst all the transfer learned models. And it also bet the performance of scratch models. So this sort of shows that if you pre-train on multiple properties at once, it can probably give rise to better and more generalizable models, right? So you use graph networks, you pre-train on multiple properties, you get fairly generalizable models, which can then be fine-tuned on any specific property with much higher accuracy compared to your scratch models. So just to briefly summarize, so transfer learning is quite useful in mitigating some of the data availability constraints and materials, and graph networks are the backbones powering transfer learning here. And we found that multi-property pre-training is one way to systematically create more generalizable models, right? So for now, we have seen that graph networks are able to give you foundational models for interdynamic potentials and are also able to give you generalizable models for property predictions. The final thing that I wanted to touch upon in my talk is generative models. Basically generating crystal structures, and these are also powered by graph networks. Okay, so if you think about classic sort of materials design paradigm, right? So we typically want a material with a given property, and the way we go about that process is we take hundreds of thousands of materials, or at least tens of thousands of materials. We calculate a lot of their properties, and then we put them through subsequent filters. So we calculate, let's say, their stability, band gap, formation energy, and so on, right? We put them through these filters, and then we get 1 or 2 candidates, hopefully, right? Which can then be experimentally validated for a given application, right? So that's the classic sort of materials design, high throughput workflow, right? Another way to think about it is in the inverse fashion. So let's say I want a material, right, with a given property. Can I generate a structure that can give me that property, right? So this is similar to asking a chatbot, right? So give me a material with so much hardness and so much elastic modulus that also looks red in color, and then your chat GPT gives you a crystal structure of such a material, right? So the general idea behind inverse materials design is that we want to generate structures that have a certain property, right? Instead of going from structure and calculating properties. So that's the classic workflow. You have a structure, you already know a structure, and then you calculate its properties. Instead of that, you want a certain property and you generate a structure from it. Okay, and in order to answer these questions, right? So basically, be able to generate a structure from a given property, we need to develop what are called generative models. So generative models generate content or generate, in the materials case, crystal structures. So how do these generative models work in the general sense? So firstly, they learn how to encode a given configuration. A configuration can be a structure. They encode this configuration into some latent space. Latent space is a sparse representation of your structure. So you learn how to represent your structure in a sparse fashion using this machine learned function given a structure. So for materials, what are the critical information within a given structure? You want to store its composition. You want to store the lattice parameters, and then the positions of the atoms. These are the 3 things that you want to store in any given structure. And what is a natural way that you can create a latent space representation of a given structure? It's to use graph neural networks. So if you use graph networks, it can automatically give you this F function here, whereby you can generate this Z, right? So with graph networks, this is a fairly straightforward fashion. Step 2 is to basically do the reverse process, is to basically decode a configuration, right? So given a latent space representation, given a sparse representation of a vectorial space, can you generate a structure from that? Can you generate a configuration from that, right? So that's the second step in any generative model. And this is, once again, something that the model has to learn, right? So given some latent space representation, the model learns this function to recreate a configuration or a structure here. Of course, any model will not be able to recreate back your original structure. So there'll always be some noise, right? Once the model learns how to encode and decode, right, given a new configuration, right, or given a new latent space representation, right, it can now be able to sample all the structures that it knows, all the structures that it has learned before, basically the probabilities of those structures, and generate a new structure. So generative models work by learning the way to encode, learning the way to decode, and then given a new latent space configuration, it then learns how to generate a new structure. This is how generative models work in the classic sense, right? And there are various generative models out there. The variational autoencoder models is what I explained actually. So you learn an encoding function, you learn a decoding function. So given a new latent space configuration here, your model tries to now predict new structures. There are also adversarial networks that you can use. There are diffusion models that you can use, and then there are auto-regressive models that you can use. Right? I won't talk about GANs. The auto-regressive models are what are used in language models. I don't think we have time to discuss language models today, but I'll try to give a brief overview of how diffusion models work in general. Okay. So what is diffusion, right? So once again, let's take an image example here. So let's say you have a perfect image, right? You slowly introduce noise within this image, right? And you see that the image is beginning to get blurry, right? Get very blurred. And then if you eventually, dump in a lot of noise, you basically get this, pixel of death, right? That people who have used older TVs will understand. Right, you just have this white noise that's appearing on your television, right? So you add in enough noise to any image, it will basically give you white noise, right? So this is what is referred to as diffusion. So you start from a fairly ordered configuration, if you think about it, to a fairly disordered configuration. Now, diffusion models not only learn how to do this process, how to add noise to a perfectly ordered configuration to get a disordered configuration, they also learn how to do the reverse process, right? And I don't know how many of you have seen the movie Tenet. So this is a turnstile representation of the movie Tenet. So you go back in time, right? So basically you go back in time in terms of denoising. So you have a noised image, and then you trace your steps back, and then you try to identify the perfect image back, right? So this is how diffusion models work in general. And this workflow can be applied to graph networks as well. And how they encode and decode your structures. The purpose of using diffusion models in materials is for structure generation, right? One of the very first implementations was actually using diffusion models with the variational autoencoder in what is referred to as this crystal diffusion variational autoencoder model, or CDVAE model. It used a complicated workflow. I won't go into the details. But the idea behind this model was given a composition and given some property that you want that composition to have, this model will undergo some kind of diffusion and generate a crystal structure. So it will start from a random structure of a composition, and then it will evolve that structure to give a more sensible looking structure with the property that you asked for. Right. So this is one of the very first implementations of diffusion models in materials. And now new diffusion models have started to spring up. So this is a study where people try to predict new high temperature superconductors. So these are once again fairly advanced materials. The authors here try to use these diffusion models to predict new structures. This is work from Google DeepMind, where they use the Unimat is basically a way to encode your structures. So this is a special form of a graph network. And then they use diffusion models along with that to generate new crystal structures, given some composition and given some property. And Microsoft has also been doing this with what is referred to as their MatterGen framework. But just to quickly summarize, diffusion models can, I think, accelerate materials discovery by generating structures that are beyond human intuition. But these models are at very nascent stages. So imagine ChatGPT 0.1 or 0.2. So they are generating bad structures as we speak. But I think we'll get better at generating very good crystal structures in the near future. With that, I come to the conclusion of my talk. So I think I gave a fairly sort of express overview of how modeling and simulations and data science has in general evolved along with material science. how classical machine learning has been used in material science before, and how graph networks has unearthed a new range of models that can be developed for material science, be it foundational interdynamic potential, generalizable, transfer learned models, and diffusion models, right? But having said that, there is a good amount of skepticism is always good to have. And the main important thing to note is that we cannot use bad data to generate or to train machine learning models. That will almost always give rise to bad models. Real success stories, I think this will be a question again. So, have there been success stories where machine learning candidates have been commercialized, deployed, and so on? Answer is no. No machine learning model has predicted a candidate material that has been commercialized. But there have been several candidates that have been experimentally validated. So this is still something in the pipeline, and I think we will get more success stories as time evolves. I think this is also another question that usually comes up. Should I do machine learning given XXX or Y problems? Don't do machine learning simply because you understand machine learning. Hammer doesn't beget a name, right? Just because you have a hammer, everything shouldn't look like a name, right? And of course, we as computational people, theoreticians, we try to construct models with care. And those of you who are interested in constructing models, please do try to do it with care and try to have enough validation mechanisms to ensure that your models are good. So with that, I hope I have given a fair overview of how machine learning is being used for advancing material science. Thank everyone for your attention. I will take questions.
Thank you so much for this engaging talk. And yeah, definitely it gave a big lay of the land of what kind of models are, more, you can say, showing some promise in material science discovery and property prediction. So there is one question which I have, and then I'll move on to a couple of others which are there in Q&A box. So my question is, when you were discussing about the GNN models, you talked about nodes representing kind of atoms and having its own feature structure. So that's the vector which is representative of set of features. For the edges, also we have an opportunity to encode and have a feature vector for the edges. Do you I didn't understand whether that is being used, because one challenge you mentioned was it cannot represent the type of bonds between the atoms. So could that be used, or is there any use of a feature vector of the edge in this scenario?
Yeah, so you can actually use feature vectors for the edges, and most of the graph networks that you typically find being developed and so on, graph networks that we use, they all use edge vectors, feature vectors for the edges as well.
Edges as well.
Yeah, so there you can take into account some amount of bonding differences. I mean, think about electronegativity differences between atoms. That gives you a very good sense of how the bond is, how ionic, covariant, or metallic a bond is. So that's usually embedded within those edge feature vectors. Distances are embedded, and sometimes even angles with respect to other edges, they are also embedded.
Okay, I'll just ask any questions because I saw a couple of them related to GNNs. Then we can move on to other topics. So there's another question which says that in the case of the graph networks, isn't it a challenge that there will be too many nodes if we are using one node to represent one atom? And how to deal with that?
Yeah, so if you have a very, very big structure, let's say 2,000 atoms, 3,000 atoms, and so on. Yes, the graph networks can become fairly heavy, and they can become fairly memory intensive, right? So if you think about the maze model that I had mentioned before, a foundation model, as we speak, it can run fairly well on GPUs, and if you were to train on 1,000 atoms, it works relatively well without any major issues. But if you start scaling up the number of atoms, I think the highest size that it has been demonstrated is about 10,000 atoms or so, which is not a lot actually, right? So there are those limitations that are out there with respect to the memory usage, the memory footprint of the graph network as you increase number of atoms. But I think those are sort of computational issues. They are not framework issues. So I think those can be solved with some degree of parallelization and some degree of maybe coarse grading. that we can introduce,
Mhm.
right? So I think these will be implemented in the near future to solve these computational bottlenecks more than sort of framework type bottlenecks.
Got it. And then there's another question: which model can you use to create oxygen vacancies prediction?
Right.
And what would be its efficiency?
What about DEET? Sorry.
How efficient would that model
How
be?
efficient? Okay. So if it is if you think about oxygen vacancy formation in a specific class of material, so that could be like a perovskite, that could be like a rock salt oxide or layered oxide and so on. If it is just one class of oxides, then simple models are sufficient. Simple linear regression or slightly non-linear models are sufficient, right? But if you want to predict vacancy formation over a large range of materials, right? Like, you want to include spinels, you want to include layered compounds, you want to include perovskites, you want to include rock salts, everything, every oxide that can potentially form. Then you probably need graph networks, and you probably need to train either use a generalizable model or train a graph network from scratch to predict the vacancy formation.
Okay.
I hope that answered the question.
Yeah. Okay, then there is another question, which is more on the generative models. So
Yes.
the question is there a generative model based on work around discovering latent knowledge?
Sorry,
That
work around discovering, sorry?
Is there a generative model based on work around discovering latent knowledge, that is word embeddings, from
Okay.
material science literature?
Right. So I didn't talk about language models and their use in material science, and people have implemented language models so far. I'd say there are two major fronts that people have tried out with language models. One is trying to predict crystal structures in the form of CIF files, so crystallographic information files. So those are basically text files, and you can easily find, like, hundreds of thousands of those text files lying around, either computed or experimentally characterized. So these are text files, and people have generated language models on those text files to predict a structure. So let's say you give this language model a composition, right? It will try to predict a text file that is representative of a real structure, right? With that composition, and that, I think, works relatively well. I haven't seen examples of very bad crystal structure generation. Of course, you will always have edge cases, but it's not too bad. The other major work that people tried out with language models was in trying to predict synthesis recipes for making new solid state materials. So let's say computationally you come up with a new material. So that could be something like calcium, calcium strontate, right? The CaSr2O4 or something like that, right? Very, very new crystal structure. Now, a solid state chemist may not immediately know how to make that material, or a material scientist may not know, right? So this work tried to scan through experimental literature, basically papers, which have documented synthesis recipes of other solid state compounds, right? And then given a new composition and a new structure, right, it will try to predict a synthesis recipe. So what should be the precursors you should use? What should be the proportion with which you should mix them, and what kind of heat treatments? How much should you heat them? How much should you cool them, and so on, right? In order to get a new material. And this type of workflow has had some limited success, but also a significant amount of failures. And this is largely because experimentally we only tend to document the success stories.
Yes.
So let's say we synthesize a new compound, we only document the precursors that worked well for making the compound, not the 100 precursors that failed, right? Because of the lack of failures, the models do not know how to train themselves very.
Yes, very good point.
Yeah. So that is still a work in progress in terms of predicting, like, synthesis recipes from known experimental literature for a new compound and stuff. That is still a work in progress.
And that's why absolutely it's so important to also document your failures digitally, so that can be leveraged in actually training more robust models.
Yes.
So similar, like from Prasad, there's a question: how the accuracy limits are achievable compared to conventional modeling? Conventional as in, not simple, experimental, conventionally.
Yeah. So once again, if you think about simple models, right, they almost always work well when the data set size is limited. Right, so if you are dealing with a data set of 100 points, 200 points, and so on, probably a simple model will be better. It'll probably fit well, and it'll give you reasonable predictions within that space that you have trained that model on, right? But as you keep increasing the complexity of your data set, so if you want to make predictions on multiple materials, right? If you want to predict multiple properties of a given material, right? Or if you want to generate newer structures and so on, then almost always the complex models win over. Simply because they have, if you think about it mathematically, they have more parameters to fit, right? So they can achieve higher accuracies on principle, and also they do practically compared to simpler models. So if you are dealing with very, very small data sets on very specific class of materials, simple models are great, and they have a degree of utility there. But if you want to create fairly larger scale models, model very different types of materials or different properties of the same material, very different properties of the same material, then you probably need complex models, deep learning models.
Okay, thank you. Okay, there's one more question which I'd like to ask. So, as your group is working a lot on machine learning at the intersection of material science, I wanted to understand, like, what is the most challenging phase of training a model? Is it like just the sheer data selection, collection, cleaning? Is it more about feature engineering? Is it about actually model training or testing and validation? So where do people tend to spend, researchers spend more time, and which area is most challenging, and what could be, ways to go about it?
Yeah. So, I mean, in India, I think this is true for all computational modeling groups. It's the data collection that's almost always the bottleneck. Simply because we are also resource constrained, right? So we have limited access to computational resources, so we can the speed at which we can generate data by ourselves is limited, right? So we spend most of our time generating very good quality data. I mean, this is on top of whatever data sets are available in public, right? So we spend a lot of time generating and curating our data set. And then that's the main bottleneck. The second, I would say, bottleneck is our access to very good quality GPU resources. Because if you look at some of the advanced GPU cards like A100s and so on, there are still very few places in India where you can get access to those cards. And many of these graph models, which are very good, they require GPUs to train very well. I mean, you can also train them on CPUs, but the training time is like, an order of magnitude higher.
Yeah.
So if it works on 7 hours on a GPU, it will take 7 days on a CPU, right? So that's the second, I would say, big bottleneck when it comes to sort of our time. So, and both of these bottlenecks are tied together. It's basically access to computation, access to good quality computational resources. So you want access to good quality CPU resources and also good quality GPU resources, which are still under development in India. So we don't have it at the scale that let's say European Union or US have it.
Yeah. Okay, great. I mean, thank you so much. I think we are almost on the time. There's a question: is it possible to get the recording of the session? All recordings are shared. They'll be on YouTube. Any other last question? So thank you so much for your talk. I mean, there were a lot of learnings around graph neural networks, especially the concepts of message passing and equivariance. That is why, where the advantage comes for graph neural networks. Then we learned about transfer learning and its importance in giving us a better result rather than doing training from the scratch. We talked about generalized models and then about generative models, which was another question from the previous session. And then, the whole process of how we leverage diffusion during these generative models. Very good talk, and very excited for what your group is doing and, really making a difference for the material science domain in India using machine learning. So thanks for that. And over to you, Professor Surya, in case you would like to the closing.
Thanks, Rapti, for such an enriching discussion. So advancements in material science are crucial for innovation, particularly in energy storage and harvesting, we got to know today. So key to developing high-performance batteries is optimizing electrodes and electrolyte materials, and machine learning is certainly playing a major role in accelerating this process. So, Sai, you nicely discussed how these techniques help predict material properties, model complex phenomena, and enable inverse design for optimized materials. So, thanks a lot, Sai, for educating us and what machine learning and AI can do in the material science field. So, thanks once again, and thanks, Rapti.